Welcome back to another session of physical sciences, specifically chemistry. I think when you see me, you know it's chemistry. So we're going to carry on with chemical equilibrium. The last time that we did chemical equilibrium, we looked at the definition of chemical equilibrium. We unpacked, we spoke a little about closed system, open system. We looked at reversible reactions. And we also looked at the definition of chemical equilibrium. We looked at the definition of dynamic equilibrium. And we looked at the graphs. On the graphs, we specifically looked at the rate graph. And I started to introduce the graph, which we call the concentration graph. So what we want to do today is, we have now spoken about what chemical equilibrium is, what the features of a chemical equilibrium and dynamic equilibrium is. I want us to now embroider on it and go and look at what happened to the concentrations, the changes in the concentrations while we are doing these reactions, the forward reaction and the reverse reaction, and what is the constant. And we call this constant Kc, but it is actually called an equilibrium constant. So in this session, we will look at the equilibrium constant and what it is, and then in a later session, we will look at the calculations, how we calculate this equilibrium constant. In short, we call this equilibrium constant Kc. I used to say that it's a goal because of all this change, forward or reverse, becoming bigger or smaller. We call it Kc if we use the short name. The terminology that we need to think, and what I'm going to use now, is things like yield. Remember, yield is what gets formed when reactants react. We're going to look at, is it a lot that formed for the reactants, or is the yield less than the reactants, or what was put in? We're also going to look at this equilibrium constant expression, and we are going to look at this equilibrium constant value and how we work this value out. That brings us to the definition of equilibrium constant, as we said, Kc. Kc is the ratio of the concentration of the products compared to the concentration of the reactants in the equilibrium mixture. It must be at equilibrium. And this value holds for a specific temperature. This is very important for us to remember, and for a specific reaction. So what do we actually say there? Say, for instance, we have a reaction, and this reaction is happening at, let's say, 200 degrees Celsius, and we find out that Kc has a value for that specific reaction at 200 degrees Celsius. If we will change this temperature to 250 degrees or to 180 degrees, as soon as we change the temperature, your Kc value, this constant, equilibrium constant, will change. So it's very important to note at this point already that your equilibrium constant, your Kc, is sensitive to temperature. It only is affected by temperature. When we look at Kc expression, we use the concentration of the reactants and the concentration of the products. I just want to remind you again that concentration is the number of mole per unit volume. We use the square brackets for concentration, so this is the concentration of hydrogen. And when we work on the Kc expression, we only use aqueous solution and gaseous solutions. We do not use the liquids and the solids because liquids and solids have a constant concentration. we normally use a 1 to represent their concentration. The Kc value gives us an indication of the yield of a reaction. And because it is a ratio, it does not have any units. We have an example in front of us. We're quickly going to look at the production of ammonia again. Remember, I said that the reaction must be balanced. So when we use the balance reaction and do the ratio or to do Kc, we always put the products on top and the reactants at the bottom. Now, firstly, you need to see that there's a coefficient of 3 there. There's a coefficient of 1 that we do not have to write. And we have a coefficient of 2. Now, when we do the concentrations of this in our Kc expression, we normally use the coefficients and it becomes a superscript. So we actually go work out, in this case, we now have NH3, the concentration to the power 2. That comes from the coefficient. For hydrogen, it's to the power 3 or to the exponent 3. So your coefficient becomes your exponent. As I said, we have for the ratio, remember this is a ratio, there's no units, we have the product concentration over the reactant concentration. For Kc, for us, because Kc gives us an idea of the yield, when Kc is bigger than 1, smaller than 1, then we always say there's more reactants than products. I always say then the denominator is big and the numerator is small. So we have this division and it will always have a number smaller than 1. When Kc have a value of bigger than 1, we know that we have more products than reactants, so we have a big numerator over a small denominator, actually ending in a number bigger than 1. Then again, I just want to stress that Kc value is only affected by temperature. Only when temperature changes, our Kc value will change. If we look at the last one, we have another example there of hydrogen peroxide that decomposes into water and oxygen. We now see we have a liquid there, and we know that a liquid has got no concentration, or we use a 1 there, and we do not include it in the Kc expression. So my Kc expression here will be the product concentration over my reactant concentration. I do not use the water because water here is a pure liquid. Remember that the coefficient becomes the exponent. And this brings us to what we call a break. Go and enjoy the break. See you soon.